Okay, so in the previous lecture, we introduced the notion of a vector. We introduced the terminology for describing a vector and its elements, its dimension, and we briefly touched on possible applications of storing data as a vector. In this lecture, we're going to begin by reviewing the standard vector operations that we touched on at the end of the last lecture. So this would just be your basic operations. Okay, so let's start with the vector addition. So two vectors of the same dimension can be added together by adding the corresponding components of the vectors. Or not components, elements, or same thing basically. And this will result, so two vectors of the same dimension can be added together by adding the corresponding elements to form a new vector of the same dimension. Or size, same thing. Dimension, size mean the same thing. Okay, so as your textbook has a few examples, we can look at maybe 0, 7, 3 plus 1, 2, 0. So we can indeed add these two vectors together because they have the same dimension. They're both 3 vectors. And we do this element-wise. So 0 plus 1, 7 plus 2, and then 3 plus 0. Okay. Now, subtraction can be done in the same manner. So, for example, you have like 1, 9 minus 0, 4. This is just going to be 1 minus 0, 1, and 9 minus 4 is 5. Okay. Now, vector addition, as I mentioned last time, we can think of this pictorially by adding the head of one vector to the tail of another. So maybe let's pick like 1, 2 plus 3, 1, or something like that. All right, so algebraically, this is just simple addition. But pictorially, what's going on here? So if we root each vector, so we'll call this maybe V and W. So V can be represented by the ordered pair 1, 2. So actually, I'll make these a little bit bigger. So all right, so V go over 1 up 2. So this would be V. And then W 3 1. So there's W. Now pictorially, if you wanted to look at V plus W, you can take W, pick it up, and attach the tail to the head. So somewhere like up here maybe. But we know where it's going to land, 4, 3, so 3, 4, and then up 3, so it's like, and that does look about right. This would be V plus W. Oh, this is W right here. This that's V plus W. So a lot of these notions with vectors have an algebraic point of view, but then they also have a geometric point of view. Okay. So I encourage you maybe to kind of draw this one. Look at the subtraction. How does that work? Well, it's basically flipping around, and you'll see that when you do the example. Okay, so what are the properties of vector addition? So vector addition, is both commutative and associative. Okay. Commutative. So commutative just means that A plus B is equal to B plus A. And associative. Which means that A plus B plus C is equal to A plus B plus C. Okay. Now, it might not seem important right now that I'm saying things like commutative and associative, but unlike scalars, when we get to dealing with things called matrices, you can't take the order for granted, right? It's not always the case for things that we will encounter that these things will hold. So when I write this stuff down, you should make a note in your head like, okay, vector addition, I'm allowed to do this. I'm allowed to do this. Because eventually you won't be allowed to do that. It won't be necessarily equal. Okay. So what else can we do? Vectors can also be multiplied by a scalar. Okay. So also be multiplied by scalars. Okay. This is done by multiplying each entry in the vector by the scalar. Each element of the vector by the scalar. So, for example, 2 times 2. You multiply each element of this vector by 2. So this would be 6 to -4. Okay. Now, with respect to scalar multiplication, so scalar multiplication it is commutative. The ordering doesn't matter. So among other properties that I encourage you to read in the textbook. Among other, I'll say natural properties that you're used to. Such as the distributive law and things of this nature. That you can think, when you're dealing with scalars, it's typically, it's just what you would imagine. It's what you're used to. So like 2 times that vector is the same thing as saying, doesn't matter. This is commutative. So maybe I'll just write that out. So alpha times A is equal to A times alpha, where alpha is a scalar. Okay, so once, hopefully, actually, I should probably do the geometric picture of this as well. I did that here. So let's look at the vector 1, 2. So 1, 2. And if I multiply this vector b by 2, maybe 2 times that vector, that results in that vector. So where does that land? 1, 2, 1, 2, 3, 4. Basically, in this picture here, it doubles the length. So if this was v, this is 2v. The line's not straight, but it should be. It should be a straight line. And a half of v would have made that vector. 3 times v would have been further. Negative v would have flipped it around. So again, scalar multiplication stretches or compresses or reverses the vectors geometrically. Vector addition combines vectors in this tail manner here geometrically. Okay, so now that we have defined or brought up the notions of vector addition and scalar multiplication, we can look at some important combinations of vectors. And which ones did I pick? Oh, this is just like, okay. And you know, it's very important, this definition for data scientists. Okay, so if A1 through dot, dot, dots to AM are in vectors, and beta 1 dot, 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 beta m are scalars, the vector or the n vector beta 1 times A1 plus dot, 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 plus beta M times AM. So that is a vector. It's a scalar times a vector plus a scalar times a vector plus a scalar, all M of them. So this N vector is called a linear combination of the vectors A1 through AN.
Does n vector just mean vector of length n?
Yeah, I would say a vector with n elements instead of length. An n vector, the number of elements in it is n.
Gotcha.
But that's a 2 vector. This is a 3 vector. The reason why I make that distinction is because vectors do have geometric length, and we'll get to that in a later section. So I think the appropriate thing would be to say dimension. So an n vector has dimension n, or you can say an n vector has size n. Try to avoid length until we start to actually talk about length. But this is important. This is a linear combination of those vectors. And this is something that you will just, as data scientists, you will encounter a lot in your regression classes. Regression is all about linear combinations. When you take your machine learning course with me later, like in your senior year, the input signals that we get from data will be taken in as linear combinations of vectors like this. This is fundamental to many regression and classification techniques that you'll learn. This is probably the first time you're seeing it. So it's kind of a special moment for you guys. Might not feel like it, but it's a big thing. Okay. So while we're on the topic of linear combinations, we should probably focus our attention on a few special cases. So special linear combinations. Okay, so what are these? So if B1, not B, beta 1 equals dot 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 equals beta M, if they all equal 1, then this linear combination is just the sum, right? This is the sum of elements, or the sum of vectors in the list. Okay. If beta 1 equals dot 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 equals beta M is equal to 1 over M, then this linear combination is going to be the average vector. and I can just write that over here as, so you can see what it looks like. So the vectors have elements in them, right? So if you have a bunch of vectors and you have like m vectors, right? It's like you're taking averages over each entry, right? Like, so maybe I should do an example with this one. So if like your set of vectors was like, so like that's your set of vectors, and you take this linear combination of these vectors, so m here is what? There's gonna be 3 of them, 1, 2, 3. So your choice for m is 3. So then, if you do 1 over m, which is 1 over 3, so I'm going to go ahead and just write this as 1/3 of, so we'll have 6 there. Oh, it happens to be 2, 2. So that was probably a bad example, but the average for the second entry is 2, and the average for the top entry, maybe I'll make it different. Maybe I'll make this 2, just so it's a little bit different. So 2, this would be a 7. So 7/3 is like 2.5 or something like that, a little bit higher, whatever. So the average for this 2, 2, 3 would be whatever that number is there. So the average vector is like a way of taking a bunch of averages at one time, right? Okay. So what are some other ones? Very, very important ones. Next. Okay, so if you sum all of these the betas together, so like b1 plus dot 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 plus bm, if those betas add to 1, that's a very special type of linear combination of the vectors in your list. If your scalars sum to 1, then this linear combination is called affine. Affine. I've heard it pronounced in a few different ways. So affine combinations are very important. Why would that be important? Well, maybe I need to write down the next one first. If in addition, all betas are non-negative, the linear combination is called convex. So one way to think about this is that, so if the betas are all, if you sum them and they equal 1, and if they're all non-negative, then you can think of this as like a weighted percentage of your vectors. So for example, like 0.12 times plus, let's say, so what is that? So is it 8? Plus 0.10 times this. So notice how like you can think of these as like, this could be thought of as like 12%, this can be thought of as 78%, this can be thought of as 10%. You can think of this linear combination as somehow weighting the vectors and taking percentages of them that you want to add to 100%, which is the 1 there. Okay. And these convex and affine combinations are so useful that you'll see them over and over again as well. All of you will have to take a course called Operations Research or Decision Math. In both of those courses, you'll look at something called linear programming, which is, in a sense, looking at convex combinations of vectors. Okay. Looking at how these yeah, it's something you're going to run into quite a bit. But I guess maybe that points to like a bigger thing. This right here, you can think of as like a weighted sum. And how people choose to weight that sum, how people choose the scalars, it varies by the application, but all of these are examples of weighted sums of the vectors. And when you do that, the corresponding entries that you get in the resulting vector is a weighted combination of all the previous data that you had. Okay. So let's look at maybe a specific example. So let A and B be some n-dimensional vectors, so vectors with n elements in them. The n vectors consisting of r from, like, these are real value vectors. Okay, so each element is a real number. And okay, so under this assumption, the affine or affine combination C, no, I'll write it here. C equals to 1 minus theta times A plus theta times B describes a point on the line passing through A and B. Okay. And if 0 less than or equal to theta, less than or equal to 1, then this point is on the line and between A and B, not just on the line, but in between A and B. Or another way of saying that is that then C is a convex combination of A and B. So, how can we kind of like study this definition? Why would it be important? So, this form though is it's just everywhere. Maybe we can take some specific examples and look at it. And to do this, I'm gonna have to draw a pretty good plane. All right, so let's look at some arbitrary vectors A and B. I don't know, I'll pick one, like maybe 1, 3. So that'd be A. So A is equal to vector 1, 3. And maybe B would be 1, 2, 3, 2. Okay. Okay, so let's look at a convex combination C of A and B. Okay. So in order to do that, we probably need to make like a table. So theta and then C. And C is always going to be equal to 1 minus theta times A plus theta times B. Okay. So, and we're gonna make this convex by saying that 0 is less than or equal to theta, which is less than or equal to 1. Okay. So what happens when theta is equal to 0? What's the resulting vector C? When theta is equal to 0, what happens? This is the 0 vector, and then 1 minus 0, so it's just 1 times A, it's just A. So when theta is equal to 0, C is the vector A, 1, 3. So we're like here, 1, 3 is right there. Okay. What about when theta is equal to a half? So I guess we'll work it out over here. We'll probably need to do some more computations so you can get used to this stuff. So if theta is equal to a half, right? So then C is equal to 1 minus a half, so a half times A plus a half times B. What is A? A is 130. And what is B? B is 3, 2. So we have the vector 1 half and then 3/2 plus 3/2 and 1. Right? Because scalar multiplication, you multiply each element in the vector. So now we add these together. So we get 3/2 plus 1/2, so 4/2 or 2. And then we have 3/2 plus 1, so that's 3/2 plus 2/2, so 5/2. Like that. So 2 5/2. So 1, 2, and then 5/2 is like 2.5, so it's like right there. That's a pretty good drawing. It's not perfect, but and notice that what's happening here, there is a line connecting these two vectors. There's a line passing through these. And the convex combination, as long as we put theta between 0 and 1, the convex combination is always going to lie on that line. Right? Basically, because if we're picking between 0 and 1, we're scaling back A and we're scaling back B in such a way that we'll land there. So the resulting vector was 2 5/2. 5/2. And I'll leave it to you to pick another value, like maybe do like 3/4. What happens when theta is 3/4? Find out the vector goes right here, and then plot it, and see that it does indeed land on this line. And then if you want, pick like let's see. Pick like 2 for theta and see where it lies. Is it going to lie over here or over there? But it will be on that line. Okay. So convex combinations are very important because of this fact here. This tells us that a convex combination is going to lie between those 2 points. So that's important when we get to our study of optimization, in the sense that if we have some function that we're studying and we have 2 points on the graph of that function, if we look at a convex combination of those vectors, like that make up those points, we're going to always lie on this line. Notice that line is always above that function, so we can somehow say something about there being a minimum below those points. It's kind of a vague way of saying it, but convex combinations tell us when we can look to convex graphs and shapes in space, which in terms of optimization is very important. In relation to data science, a lot of what you're doing mathematically is optimizing things, solving optimization problems. So when I mention things that are tools related to optimization, you should make notes and like really try to understand it the best you can. Okay. So on to our next major yet basic vector operation. So we looked at scalar multiplication, vector addition, and we've shown how these notions can tie in together, averaging things, summing things, finding points on lines connecting vectors. The next operation is what's known as the inner product. So the inner product, also called the dot product. of two n vectors is defined as the scalar so we have two vectors A and B. This is the dot product or the inner product. It's the sum of the products of their elements, component-wise. Okay, again, fundamental thing, fundamental operation that you will see over and over and over again. Let me just go ahead and give you like a worked out example. And that capital T that I keep on drawing, we will come back to what that means later in a section down the road. For now, just know that whenever you see vector raised to the T times another vector, that is the inner product. And how does it work? Well, again, as I mentioned a second ago, it's summing the element-wise products of the two vectors. So this would be -1 times 1 plus 2 times 0 plus 2 times -3. Whatever that value is -1 minus 6, so -7. So the inner product of those two vectors is given by, is the scalar -7. Okay. Okay, so as I mentioned before, when we're defining operations on vectors and matrices and pretty much anything in this class, we do need to make note of the properties that these operations obey. In particular, the inner product is commutative. Which basically means that A transpose times B. I said it out loud. That T means transpose. We'll learn what that means later. But just the inner product of A times B is the same thing as the inner product of B times A. So it's commutative. Okay. It is associative with respect to scalar multiplication. Yeah. To multiplication. Basically, just saying that if we have some scalar gamma times A times B, that's the same thing as saying that scalar times A times B. And then finally, it's distributive. Not finally, but these are like the major points that I want to just emphasize. You'll see other properties in the textbook, when you look at the homework that I'll assign later. And all this says is that A plus B times C is the same thing as A times C plus B times C. Those are the fundamental properties of the inner product. There are more, and you will see those in the homework. Okay, so maybe we should look at an example of some common inner products that you might see in data science. So one would be this. Okay. So what is that? What is this EIT again? Or not EIT, but what is the vector EI? So this is the vector with 0 everywhere except for a 1 in the ith entry. So you can take the inner product of that vector with A, and then it will select out the ith entry from the vector A. This is why last time I referred to this vector sometimes as like a selector vector, because it'll pick out the element that you want, it'll make everything else 0. So maybe like, for example, like E2 t times maybe 1, 4, 7. This is the vector 0, 1, 0. Still times that, 1, 4, 7. So then that times that is 0, plus that times that, plus that times that. This is just 4. And you see that it selected out the second entry from that vector. Okay. The ones vector times A. This is just the sum of the entries in A. The A is just some n vector. The one vector times that is just 1 times A1 plus 1 times A2, dot, 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 1 times AN. And then, sum of the squares. So A, inner product A. This is just A1 squared plus dot, 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 plus AN squared. So sum of the squares in the of the elements. Now, now that we're getting to this type of notation, I need to warn you about a certain confusion that can happen when you're first starting to learn about vectors and these various sums and products. And that is that previously I wrote down a list of vectors, A1 through AM, and then I just did the same thing here. These are not vectors. These are implied to be the entries from A. These are implied to be the entries from A. They're not vectors. There is a notational inconvenience that happens with vectors. But it should be clear from the context that that is an entry from A being squared. Right? This is just it's just squaring those entries. They are not themselves vectors. Okay. So the sum of squares will happen a lot. This is something that you'll see, especially when it comes to regression. And in particular, one that I didn't write down over here, but you will see is something that looks like this. This is, you'll see that a lot. And that's all it is the inner product of of a vector W with a vector X, but this is often a weighted sum of the elements in X. And I'm going to go ahead and write it in parentheses, features. In X. So X could be like a data point, vector, and each of the entries in that vector can be a measurement of something. Like for example, you could have like X being the first entry being like your total income, second entry being your age, third entry being the amount of debt that you have, the fourth entry, are you a homeowner, so forth and so on. And then the weights here can correspond to how significant each of those entries should be applied to maybe your credit score. So then this weighted product would be like a score on your financial information. It's just a compact way of writing it. Instead of writing out the whole list of information, we write it simply as the inner product. When you're feeding information into neural networks in machine learning, the information signals that you take in are in the form of inner products. This you can think of like maybe like a computer vision scenario where you have a still shot of something like a cat or a dog, and that's a bunch of pixels, and you take in a weighted combination of all those pixels to tell whether or not some pixels are more important than others with respect to classifying a dog versus a cat. This is fundamental to just data science. It's the inner product. Okay. So now I'm going to go ahead and stop the video here, and then this will conclude the basic operations lecture that we have.